just where we are. Okay, so right, okay. So we've gone through the motivation. We have described the branch flow models, different models with different assumptions, and a very efficient method to calculate power flow solutions. And then we describe the linearized model, is some of its nice analytical properties, and then use it to look at a local control for voltage, for stabilizing voltages in distribution systems using this linearized model. So this is just an illustration of how linearized model can be used, making use of its analytical properties. So those are the models. And now let's look at, we can define OPF using this model as well. And they're also for single phase SOCP relaxation. And then we look at a two-bus example very carefully to understand what is the structure of the underlying problem and how, say, exactness depend on the load on the network, for example. Okay, so that's the plan. Let me start. So it's good to, I think we can manage the time because I think I've included fewer materials today. So let's recap of, do a bit of a recap of what we cover and then transition into OPF and relaxation. All right, so we'll recap BFM branch flow model, in particular this flow model, and then that will also be generalized to the three-phase in the next block. And then we look at OPF in this model, exactness, and then we look at this two-bus system. So this is the disk flow equations that we saw earlier. This is for networks without cycles and with zero shunt admittances on the lines. The first equation is the power balance. We saw that before. The second equation comes from Ohm's law. You take the Ohm's law, you massage a little bit, and you take the voltage, you take the magnitude square of that complex number or equations, then you get this equation, which the key is that involve voltages without the phase information. And again, as I mentioned earlier today, that all this real complex notation, they're just shorthand for real quantities, right? All variables and equations are in the real domain. And then really the definition of branch power as Ij, and you take the magnitude square. So the important thing to notice is that the set of equations are linear in the variables, and the variables are the small s, which are the power injections, real and reactive power injections, the voltage magnitude square, the branch power flow, and the current magnitude square. So the equations are linear in the variable x, except this quadratic equality, and that is what we're going to realize later on when we do the SOCP relaxation. So that's the disk flow equation. This is linear, this is quadratic, and this was proposed back in '89 by Baran Wu at Berkeley. And compare with the bus injection model, right? So this is an example of you have different variables that you define, and they satisfy different set of equations. In what sense are these two models equivalent? So here in the bus injection model that we covered yesterday, the variables are the nodal injections, S, and also the voltage phasors, V. Whereas in the disk flow model is this set of real variables, and they satisfy different equations. And these two models are equivalent in the sense that there's a 1-1 correspondence between their solution sets. And then we looked at the lean disk flow, where if you just take the disk flow equation and set L equal to 0, then you get the lean disk flow, right? So that's the lean disk flow, which is this. And we saw earlier that it has nice properties. You can write down a solution explicitly given the injections. It has also a very simple relationship between power flow solutions of the nonlinear disk flow. Right? The branch power and the voltage bounds those in the nonlinear model. So it's more suitable for distribution systems because of compared with DC power flow because of these kind of properties. It's reasonable with the line loss, which is the ZJK, LJK, right? So this complex quantity, if the real and reactive line loss is small, compared with the quantity SJK, right? The real and reactive line power. In typical examples, test systems and SCE circuits, we see the line loss typically is small, a few percent, for example, compared with the line power. And therefore, this model is reasonable within that kind of error. Yes, explicit solutions and other important analytical properties. So this is the explicit solution that we saw earlier, and it bounds the nonlinear power flow solution. Okay, so for mesh network, then the bus injection model works for general network, whether you have cycles or not. Branch flow, the disk flow model works only for radio network. If you want to extend this to model networks with cycles, then you need to add this cycle condition. And we saw different forms of cycle condition earlier today. So this is one form. Okay, so let me so we saw earlier that what beta is. So beta is a vector of size, the number of lines, where beta JKX is given a power flow solution or given X, that this is the set of real vectors, you can compute this expression. And what this expression really is try to capture that this should be the phase angle difference across line JK. So this is a valid power flow solution for a mesh network if the given X, which contains no angle information, is such that the expression beta here, defined here, can be written as theta j minus theta k. So there exists some nodal variable theta that depends only on the nodes but not the branches. So that the theta j minus theta k difference of the two nodal variables is the beta if there is such a theta, right? So it means that beta is in the column space of B. B is the reduced incidence matrix. So that's a cycle condition. Okay. So then you can show that even for general networks that contains cycles, these two models are equivalent as long as you the power flow solutions also satisfy these cycle conditions. So the cycle condition is part of the model, part of the equations that must be satisfied by your variable X for networks that contain cycle. Okay. All right. So as I mentioned towards the end, that the models are equivalent, but the branch flow model seems to be more stable numerically, and it has also nice properties. And the important thing also for distribution systems, which we'll cover in the next block, is that almost everything that we said has a direct extension to the multi-phase 3 unbalanced system, which will be very useful for distribution systems. So that's a recap. So let's look at OPF. Okay. All right. So that's the branch flow model for general networks with cycle. Let's ignore that. Even for general network, you can do SOCP relaxation, right? We did that yesterday within bus injection model. That even for network recycle, you can do SOCP relaxation. It's just less tight, right? And typically, not always, but very often, if you do SOCP relaxation for a mesh network, the relaxation will not be exact. You will get an optimal solution, which will not be feasible for the original OPF problem. The optimal value of your relaxation provides a lower bound on your non-convex AC OPF. Now, the bound can be useful because then you can use a local algorithm for your non-convex OPF to compute a local solution. Then you can evaluate how good is the local solution. If the local solution gives you a cost that is very close to the lower bound provided by your inexact relaxation, then you're confident that your local solution is pretty good, right? So that's useful even if the relaxation does not produce a feasible solution, okay? And therefore, there may be reasons for using SOCP even for mesh network, even though it's very likely that you won't get a feasible solution. And indeed, that is some of the things that people, including ourselves, do when we deal with very large OPF problems. For very large OPF problem, if you try to solve even quarter relaxation, it can take a long time. And sometimes numerical issues for large problem instances prevents it from even converging for SCP or quarter relaxation. In those cases, if you solve SOCP, typically you can solve very large cases, even though it may not be exact. For radio networks, then most often you're going to get exact solution. Okay, and therefore whether it is for mesh network or radio network, that is whether the set of powerful equations includes a cycle condition or not, there may be reasons to do SOCP relaxation. And in SOCP relaxation, what you do is you ignore the cycle condition if it is present for the mesh network. You change the equality into inequality. That's all you do. Then you get a second order cone problem. Okay, so that's this. Right? So you ignore the cycle condition, you change that to inequality. Okay, so that's the SOCP. That's a second order cone. And OPF, SOCP relaxation of OPF within branch flow model simply means that this set of equations are part of the constraints of your OPF or its relaxation. That's what it means. Okay, so it's very simple. So the OPF means that you want to minimize a certain function, cost function F that can represent, say, real power loss over the entire network, or generation cost, or fluctuations of your voltage, deviation from voltage reference voltages. Some in the demand response applications, there's some user utility. Let's say if you change the temperature setting of your HVAC, then you might impose a cost on the deviation from the desirable temperature, for example. So all of those objectives, performance metric, can be modeled by some function F as a function of the variables in the network. So we want to minimize this cost over the set of variables X such that, say, two sets of constraints are satisfied. One is the operational constraints. And the operational constraints here is very simple, that there may be a limit on the injections. So in the context of demand response, for example, then there may be a capacity limit on how much you can generate or consume real or reactive power, right? Say, mobile control. And the second is that the voltage magnitude has to stay within, let's say, 0.5, so 5% of the nominal, for example. Right? Now, depending on the applications, there may be other operational constraints. So here I'm just keeping it very simple. So these capacity constraints on the injections, so controllable loads, for example, and the voltage constraints are important constraints that are probably present in any application. But there can be additional operational constraints, typically inequality constraints, depending on your application. The second set of constraints is the set of power flow equations. For AC model or nonlinear model, let's say this flow model, this will be nonlinear equalities. And therefore, the problem is non-convex. And what you do for relaxation is simply relax the nonlinear equalities. So into, in the case of this flow model, inequalities and then you get a second order cone for your power flow equations. And the problem becomes, assuming F, let's say if F is linear or even quadratic, convex quadratic, then you just get a second order cone problem. So, so that's the idea of OPF within branch flow model, this flow model in this case, when we ignore shunt elements and on a radial network. Then you just get this SOCP relaxation. Good. So to recap, this is OPF. We want to minimize certain costs within a feasible set that is non-convex. Instead, we will minimize the same cost over a convex superset. Okay, so and the convex superset in the case of these flow equations turns out to be a second order cone. Okay, very good. Let's see, we are doing well on time. Good. So then you can show that SOCP, second order cone program as a relaxation is exact for radial networks. So the radial network is important. If not both real and reactive power are both lower and upper bounded at each end of the line. So this is the linear separability that we saw yesterday. This holds for the this flow model as well, even though it is proved in bus injection model. Excuse me. This is where the equivalence of the model becomes useful. So it may be difficult to formulate or prove in one model than in the other, but the property holds for all equivalent models. The second sufficient condition, which I'll cover in the next couple of slides, is that roughly, so we'll see the precise statement later on, but roughly, if the voltage bounds are not tight, or if there's no voltage bound, let's say the voltage upper bound, upper bounds are positive infinity. Right now, of course, in practice, they're always the voltage upper bound. But if we know for the networks that we operate, the upper bound is almost never tight. Then in the mathematical model, we can choose to ignore the upper bound. And so infinity, positive infinity. In that case, if you have a radial network, the SOCP relaxation within the this flow model, using the this flow model will be exact. Okay, so let's look at the precise statement of what that voltage upper bound condition is. All right, so, okay, before we look at the more precise statement, I think there's a version. Let's just recap the ideas of relaxations and stuff. So today we talk about SOC, second order cone program, using the this flow model, right? Where you solve this, you get an optimal solution for the relaxation. Yesterday, we talked about three other relaxations using the bus injection model. So we can solve the SDP relaxation for the entire matrix, if you recall. We can solve chordal relaxation, which only solves for a partial matrix defined on a chordal extension of the graph. Or we can solve even for a potentially much smaller partial matrix that's defined on the graph itself, not a caudal extension, but the graph itself, if the graph is not caudal, right? And that is also second order cone program. Okay, so this tool, SOCP, in bus injection model or in this flow model, both are very, very efficient. They are more computationally intensive than linear program, but not much more. It's very, very efficient compared with SDP in general. So we get the optimal solution from, we get an optimal solution from the relaxation, one of the W stars or X star. Then we check whether certain conditions are satisfied. Right? So for the matrices or partial matrices we covered yesterday, we check whether the matrices will be rank 1, right? So whether the full matrix is rank 1, whether the partial matrix defined on a caudal extension is rank 1, which means that we have to look at the submatrices that are fully specified, the submatrices of the W star C of G, right? For each fully specified submatrix, which corresponds to a click in the graph, then you check whether that submatrix is rank 1. For this SOCP relaxation WG star, we check for every line in the network. It has a 2x2 submatrix. You check whether that 2x2 submatrix is rank 1. So if it is rank 1, then you are done. You can recover V star that is optimal for the original OPF. For SOCP relaxation here, if it is the 2x2 rank 1 and the network is radial, then you are done. For this flow model, then you get the X star, which is a optimal solution of your SOCP. You check whether VJ, LJK attains equality equal to SJK squared, magnitude squared, right? So PJK squared plus QJK. If you have equality and the network is radial, then you are done. If the network is not radial, right, then you check whether it's satisfied cycle condition. So there's a cycle condition in terms of the WG star entries. Basically, the angle, sum of the angle over any cycle has to be 0. For the disk flow model, there's this beta JKX, whether it is in the column space of the instance matrix, which means that it can be expressed in terms of some nodal variable theta as theta j minus theta k. Okay, if there is such theta vector, then you satisfy cycle condition, then you're done. You can recover Y star. Now, if any of these tests fail, like this is no, or no here, then we get a infeasible solution essentially. Then there's not much one can say except that number one, the cost provides a lower bound, and number two, you may be able to, oh, sorry, it froze a little bit. You may be able to use the solution, infeasible solution, as an initial point, and then run local algorithm, for example. Right? Okay, so all right, so exact relaxation. Okay, let me double check on time. So so we are here. Oh, okay, so I should speed up a little bit. Okay, so that's the informal. If the voltage upper bound are not binding, then SOCP is relaxation. So let me go quickly. Maybe describe this geometric insight, which we'll look at more closely in the second half of this block. So the geometric insight can be obtained by looking at two-bus system. We have a substation, V0s are given. The loads, think of this as loads. So these are given. The variables are the voltage at the low bus, the current on the line, or the current square magnitude, and then the injections at the substation bus. So these are the variables. Okay. Now you write down these flow equations and massage a little bit. You will, so these are given. These are the variables. You can write down the equations, these flow equations, massage a little bit, and then look at stare at the equation and try to see whether you can visualize it. And then indeed you could for the bus system. The power flow solutions there are two of them. Not surprising because it's quadratic equations. That is in terms of Q0, P0, and L. So in this picture, there's no V1. So once we determine P0, Q0, and L value, then V1 is simply a function of these three values. And therefore, and in fact, V1 is a linear function of these three values. And therefore, let's focus on these three first and try to understand what is the structure of this power flow solution for these three variables. And it turns out there are two solutions for P0, Q0, and L. And they are the intersection of the line that is drawn here with a parabola, right, which is given by this. Okay, so you get a bowl, and the intersection of the bowl with the line, that's the two power flow solutions. And those two solutions, once you get the P0, Q0, L, then you can substitute to compute V1. And the two solutions corresponds to, one is the low voltage, one is the high voltage. Okay, so we will see the details of this calculation in the exercise, and we look at a little bit of that in a moment. So then what is the effect of, and therefore in your OPF, this problem, the feasible set is actually just these 2 points, and therefore it's of course non-convex. It's 2 points disconnected. The SOCP relaxation, what it does is that it enlarges the feasible set from the 2 points to the entire line, which is a convex set. Okay, so that's the convex superset that contains the 2 points, and therefore it is a convex problem. Now, what is the effect of voltage bound? What the effect is the following. Oh, so V1 is simply linear functions of P0, Q0, and L. So feasible set is non-convex. SOCP enlarges it to the line, which is convex, and it is up. When will it be exact? It will be exact if, let's say, the cost function f is increasing in L, right? Meaning that, for example, if you want to minimize the total loss on the network, then you'll be increasing function in L. Then when you minimize your cost over these 2 points, then this high voltage solution has a lower L and therefore lower cost. And therefore, this will be the optimal solution if the voltage bound are not binding. And therefore, SOCP will be exact if the cost is increasing in L and the voltage upper bounds are not binding. Okay, we'll see a little bit of that. So it will be exact as long as the lower point, right, is in the feasible set of your problem, of your OPF or your SOCP. As long as the lower point, which is the high voltage solution, is in the feasible set, then SOCP resistance will be exact. Now, this is the case when the voltage upper bound is not tight. If the voltage upper bound, so the effect of voltage upper bound is that it cut off the parabola from the lower end. So if you cut off the parabola and from the lower end, but still the high voltage solution remains feasible, then SOCP, then that high voltage solution is the optimal point, and therefore SOCP is exact. On the other hand, if the voltage upper bound is too low, so it's tight, it cut off the parabola above the point C, then the low point, which is point C high voltage point solution, is not feasible. The only feasible point is the low voltage solution here. That's the feasible set of your OPF. The SOCP, though, has the feasible set, which is the entire line up to this plane that is being cut off by by the voltage upper bound. And therefore, if you minimize it, right? We minimize it, try to press down the L, then you will get a optimal solution for your SOCP, which is not feasible. That's why SOCP relaxation is not exact if the voltage upper bound is tight. So that's okay. I want to leave more time, so we're a little bit late. So let me skip the details of this more precise statement, what it is. But the informal statement is that if the voltage upper bound, okay, so I need to explain what this is. This really is the linearized, if you take the linearized model, solve for the voltage, right? So we know how we can write down the voltage explicitly as a function of injection. And in fact, it is a linear function of injection. So if the linearized voltage, which is simply a function of injection, satisfy your upper bound, then because we know that the voltage, nonlinear voltage, is upper bounded by the linear voltage. And therefore, if this holds, then the voltage indeed will be, the voltage upper bound will not cut off the high voltage solution, the point C, basically, okay? And therefore, the condition can be the no voltage upper bound or the voltage upper bound being all tight and so on, can be expressed in a more conservative way, right? It's more conservative because the voltage linear voltage is upper bound on the real voltage, AC nonlinear voltage. But if the upper bound Vlin is less than the voltage upper bound, then and then there's a Jacobian condition which I ignore. Then SOCP is exact, and this just the intuition is what we saw here. Okay, so that's that. Okay, good. So let me go to the example. So this would be Tuba's example. Okay, good. So now let's look more closely at the Tuba's system, right? So we already know the high level intuition with the Tuba system, that we can look at the variable the variable P0, Q0, and L, try to understand the structure and try to understand the effect of voltage upper bound on that. So let's look at the following in a bit more detail. So again, the key power flow equation. So this is P1, Q1 that's given, V0 is given. The variables are okay, it's still good. P0, Q0, V1, and L. Okay. So the equations are P0 minus P1.
Stephen,
Q0
are you writing something?
minus Q1. So let me write this first. And then V1 minus V0 P1 X. Oh,
Stephen, were you writing something? Can you hear us?
okay, so my iPad quit Zoom again. Let me join again. Okay, so join as panelists. And I need to set myself as a co-host, make co-host, so I can share screen. Okay, good. Oh, good. Okay. X1 minus, let me just use Z square L. Okay. Now, so this is simply the original disk flow equation specialized to this two-bus system. And the first thing is to show that instead of this, we can replace this by P0 square, Q0 square equals V0 L. Just manipulate these four equations, and then you say, okay, this one holds as well. That gives us a connection between P0, Q0, and L, right? And that's the problem that we solve. You get this thing. So that's this, and then you get these two planes, the intersection of these two planes that will give you a line, and therefore that gives you this line from the two equations here, and therefore the intersection, say, are these 2 points. Okay, so you can ask questions on, for example, so all these are in the document on the canvas. You can ask questions to say, okay, you have these four equations that define for these four variables. When will solution exist, right? So then you can massage it and so on, and you can figure out a range where for on the low P1, Q1. Right? So if P1, Q1 satisfy certain conditions, then there is a solution for the four variables P0, Q0, L, and V1. Otherwise, there's no solution. There's no real solution. Right? It's a complex number, but it means there's no real solution. Then you can look at, more importantly, let's look at the case so that we can visualize it. Let's look at the case where, say, Q1, which is the low, given low, let's say 0. So the low is DC low. And just make it simple so that, simple notationally, so that, let's say, let's say we set V0 equals 1, Rx equals 1, right? So that you get simpler equations. And then you can look at, you can ask how does V1, so you substitute these assumptions into these sort of equations. And you can solve it or implicitly trying to just prove properties without solving it. You can ask what is the relationship between V1 with the voltage we care about. We want to do mobile control, then we want to make sure the voltage lies within a certain bound, for example. Right, so you can ask what is the relationship between V1 and P1. So P1, so Q is already 0, and the load that we can vary is P1. Then we can try to understand as P1 varies, how will the voltage vary? Right, so you can look at that. And then it turns out is an ellipse. So V1 as a function of V1 as a function of P1 is an ellipse. So it looks something like this. So this is P1, this is V1. So as P1 varies, then V1 varies as well. And therefore you see that given any P1, there are two solutions. One corresponds to the high voltage solution, one corresponds to low voltage solution. Okay. And that has implications, as we saw earlier. And then you can show what is the highest voltage that you can attain, what is the low voltage you can attain, and so on and so forth. Right? And then you can also look at the impact of within a certain range of P1, there may not be solutions. Right? And then now, once we understand all this, then it's easy to deduce the impact of varying the P1 on the solution of OPF and the solution of SOCP, and when SOCP will be exact. So let me look at the time. Okay, so I probably should stop here. Let me, okay. So the ellipse that I draw is incorrect. It's not this form. V is always positive. It's actually of this form. Okay, so this is the right ellipse. Okay, so this is P1. This is V1. Everything else I said is correct. So what is nice is to say that, okay, suppose I impose my V1 to fall within, say, 5% of my nominal, which means that a valid power flow solution for my OPF, for example, must have V1 that lies between this bar. And therefore, as P1 varies, this is the only V1 that is valid solution. Then you can look at the impact of P1 on exactness of SOCP. So what happened in SOCP is that when you fix a P1, say this point, which is a load that is given, the solutions, if there's no voltage constraint, then the solutions will be this. We'll have V1 upper and lower voltage. SOCP relaxation will be this. So this will be feasible step for SOCP relaxation. Now, when you have voltage bound, what does this mean? What does this picture mean? It means that the feasible set for your OPF are these 2 points, which means your OPF is infeasible. The feasible set for your SOCP, though, is this. So your SOCP, if you choose P1 to be at this point, this certain range, your SOCP will be feasible. Your OPF will not be feasible. If you choose your P1 to be here, then your OPF feasible point will be here, will be here. Your SOCP feasible point will be this. Okay, maybe I should. Will be this. And the optimal solution will be at this point. The optimal solution of your OPF and of your SOCP will be at the same point, and therefore SOCP is exact. On the other hand, if you choose your P1 to be within this range, that's your P1, then the OPF feasible point will be this. Your SOCP feasible set will be this. Your SOCP optimal solution will be this. Your OPF optimal solution is this only point. So this is not exact. And therefore, depending on your P1, the load specified that is specified for your OPF problem, you may get a problem that is infeasible, whereas SOCP is feasible. Or you may get a problem where the SOCP is exact or inexact. Right? So that's what's going on. Okay, so common Okay, great. So you're online. I'll let you, I'll stop sharing. I'll let you introduce yourself. So Xu has done really nice work creating a set of programs that will allow you to explore what I said and much more. And in fact, her program is even more general than this two-bus system, but she will only talk about her program within the context of this two-bus system. They can allow you to see and visualize many interesting properties. Okay, thank you, Carmen.
Okay.
Please introduce yourself as well.
So I'm Carmen, and I've been helping Stephen with this two-bus example. Can you hear me well?
Yes, yes.
Perfect. So I've created 2 Jupyter notebooks, which where you can explore all these concepts that Stephen was talking about. And for those that you don't know Jupyter notebooks, you need Anaconda, and we have uploaded a video where it explains how to download Anaconda, and also you will have these files in Canvas as well with some instructions on how to download the packages. So you should be able to have these notebooks and just explore this example of the two-bus system. So this Jupyter notebook, I don't think we have too much time, so I don't want to spend too much time explaining how it works, but this is text.
So Carmen,
yes?
you don't have to rush, because
okay.
I think the next session I can control. So take your time.
Okay, so this is text. These are cells that are text. This is cells that are code in Python. And as you can see, each cell, you can put an output here, for example, here, and you can run each cell just pressing run here, or restart and run all the cells together. I have run them before this session, so we don't lose time running each cell. So the objective of this notebook is to first understand how to use Python if you haven't, and how to create an optimization problem using Pyomo. And of course, is to translate these equations that Stephen has provided into code. So the first step is you need to import packages to do this model. And then I created this table where you can see that you can very easily compare what is the solution of the ACOPF, the second order cone relaxation, and the linear relaxation for the different variables that Stephen was explaining, P0, Q0, V1, and the current. So this is the two-bus system we're trying to study. We have bus 0 and bus 1, and in we're going to solve it as an optimization problem. So we're going to model an optimization problem, very simple, and we will solve it aiming to minimize the losses, because we're doing an OPF. So the variables are P0, Q0, the current, and V1, and then the parameters are the remaining value elements that you see in this case study. So we are going to start with P1 equals 0, Q1 equals 0, and P0 equal 1. And we have the line parameters that Stephen mentioned. And we're starting with these voltage limits in this case. And once we have all this, we just need to create the optimization model. So we're doing a concrete model. This means that the parameters are directly defined in the model, as we've seen here. And once we have created the model, we're calling the model M. We can move on to define the variables. So as we can see here, the variables are P0, Q0, current, and V1. And this is the syntax that you need to use, M, to say that it's a part of the model M. We just define P0, the name of the variable, is equal to a variable. And then we do the same for the remaining variables. And for the current and voltage, we're defining some bounds. So we're saying that the square current needs to be between 0 and the maximum current, and the square voltage needs to be within the bounds of V1 min and V1 max. So now, once we have the variables, the next step is to model the constraints, and you can see them here. This is exactly what Stephen has just showed you. And in here, because V0 we're considering equal 1, the ampacity limit is an equality because it's an HCOPF and we're not putting V0. If you wanted to make more general, you should consider here the voltage. And those, as you can see, with Payomo, we essentially get to write the equation in the constraint. So the P balance equals a constraint with a rule that is P0 minus R times the current equals to minus P1. And that's the same process to build all the constraints that are here. We don't need to build these constraints because these constraints have been already put in the bounds of these variables. And once we have created constraints, the last step is to create the objective function, which is to minimize the losses. So M squared, the variable of the current times the resistance, and we want to minimize them. Once this is the end, we have our optimization model created, variables, constraints, and the objective function. And the last step is to solve the problem. We need to use a solver. In this case, we have used IPOpt. You have the details on how to get the solver running, and it's completely open source and free. So you all can use it. And yeah, we get the results. And then what we do is that table, which is a data frame that I created before, we're just saving the values of the decision variables. And we put it in the correct column, in this case, HCOPF, and we see that as it's P0 equals 0, Q0 equals 0, V1 equals 1, and the current equals 0. And if you did the analytical, solve it analytically, you would get the same answer. Now, the second order current relaxation is going to be the same process. The difference is this P0, Q0 equal to L, now it's an inequality. That's the second order current relaxation. So essentially all the same, you can see here, we're putting the inequality, but it's the same process, same variables, same constraint except the line ampacity. And then we solve the problem here and we save the values. And again, in the data frame, we can compare now HCOPF and the second order current relaxation. And for this value of P1 and Q1, second order cone is exact. The last relaxation that we have in this Jupyter notebook is the linear relaxation, in which we don't have the current to make it linear, and the optimization problem is modeled by these constraints here. So also one thing that I did in this cell, I relaxed the voltage limits because in the linear relaxation many times, if you put those voltage limits I put before 0.95 and 105, you will have an infeasible solution. So in here I'm relaxing them. And the same process, this is even simpler because we have less constraints and we don't have the current. And for the last step, we have an objective function that we don't have the current, so we cannot minimize losses. So because this is the solutions that satisfy the constraints is trivial. There is only one solution. The objective function definition is not too relevant, so we just decided to put P0, minimizing P0, and we solve the problem in the same way. And finally, we get the solution, and we can compare the HCOPF and the other two relaxations. And we see in this case, in the linear end, we have doesn't apply because we're not modeling the current. But in this case, they are all exact post relaxations. And then here there are some test cases, examples of things that you can do. And just to show, we can just get a different value. Now P1 equal to 1, go at the top where we define it, paste it, and then we restart and run everything. And this will take us to the end of the notebook. Yeah, there it is. And in a few seconds, it will provide us the results. Here it is. And this case for P1 equal 1 and Q1 equal 0 is the cases that Stephen was just explaining, where second order code relaxation is not exact and linear isn't either, but it's going to the upper bound limit that I put of 1.05 squared. Okay, so this is this notebook is more for you to understand how to model this problem and have a very simple example, but you will also have access to another notebook, exercise 2, which with the exact same model, we explore more interesting examples of what Stephen was explaining, and you get to also see graphs on what Stephen was explaining, and he created some nice examples that I've implemented in this notebook. So the same steps, we need to import packages, we need to create a data frame, empty, and now to make it easier to do many examples, what I'm doing is to create a function with the exact same model that I just presented. So that way we can call just this function here, and with one single line of code, this whole model will be run. So that makes it easier. So we do that for the ACOPF, we do that for the second order cone, and the linear relaxation. So the details on how to model it is in the previous network. Here it's considered that this is understood. And just to validate that we did everything correct, we give the same problem parameters as before, P10, Q10, V01. And as you can see, we just need to run 3 lines of code and we get the same table as before and the same results. So now that we have that, we can move on to see some interesting examples. The first example is to see if, or to show that this is the feasible range of P1 between these 2 limits. I'm relaxing the voltage limits because now we're not interested in an actual real case where you will have a voltage limits in your network. It's more a representation of the behavior of the ACOPF and the relaxation. So I'm relaxing the voltage limit, and I put P1 to have a value lower than the lower bound, and I run the ACOPF, and the solution is that it's infeasible as expected because it's not in the range. I do the same with a value larger than the upper bound. I run the ACOPF, and again, it's infeasible. Now, if we check a value within the bound, for example, 1.1, we do get a value, ACOPF is feasible, we get a value, and here you can see why I relax the voltage limits, voltage is close to 2. So we have shown that the feasible range of P1, and we will see it further in the following example. So in the second example, we want to show that for each value of P1 in the range, there are 2 voltage solutions given by this equation. So the first thing that we're going to do is just take that range that we saw here and create an array with those values that iterates in these values with a step of 0.05. This is the array that I created. And then I'm just going to do a for loop in this P1 P1 range array and calculate the value of the voltage, the high voltage solution as the low voltage solution, using that equation here. And then we plot it and we see that effectively it's a rotated ellipse as we expected. And I'm going to do the same with the optimization model that I created to confirm that the optimization model is behaving as expected. So the process is the same as here. We create a P1 range and then iterate, but now instead of calling a function, now instead of calling the equation, I'm gonna call the ACOPF function. So if we don't constrain the upper bound of the voltage, so if we put, for example, V1 max equals to 4, we are going to get the high voltage solution because that minimizes the objective function. It has lower costs. So by doing this voltage limit maximum equal to 4, essentially we're going to get the high voltage solution. So I run the for loop for the different values of P1, and I save the voltage solution in this object here, and we can see how the voltage solution, this is the result that we get from like over 30 optimizations. And to get the, so now we have the high voltage solution, which will be the same as the equation. And then to get the low voltage solutions, we have to do the same, but we have to put a smart limit on the upper bound of the voltage, because as you can see, yes, it's not constant, it needs to be aligned. So this is what I do here. And I create a dictionary where for each value of P, we have a upper voltage limit that changes as P changes. And we do the exact same thing, but in this case, where each iteration we're changing the upper voltage limit, and we call the ACOPF, and in this way we get an object with all the low voltage solutions. So the last thing to do is to plot it. So we have the high voltage solutions and the low voltage solutions from the optimization model, and we see that it has it has the same shape, the same values as the ones in the equation, and we have the high voltage solution in blue and the low voltage solution in green. In this third example, essentially you need to explore the high voltage and low voltage solutions to find the minimum voltage. So the minimum voltage in batch 1 is 0 for P1 equals 0. That is here in this point. And the high voltage, the maximum voltage, you need to explore the high voltage solutions that you saved, and the maximum voltage is 2 for P equal 1. We can see it here too. Now the last step is to compare the second order cone and the ACOPF, like Steven was explaining before, and when second order cone is exact, we're establishing voltage limits here. So this is the voltage limit that I'm establishing according to the statement of the problem. And we do the exact same of running for loop for each value of P1 in the feasible range. However, we know that with these voltage limits, if we go here, for example, for minus 0.02, P1 equals minus 0.2, there is no voltage, it's not in the feasible set for the ACOPF for the second order cone. So we know it's gonna be infeasible. That's what I'm adding in this extra line to not save the infeasible results. And that's why we get here some infeasible results. But we get also feasible results that we will see. And here is the final result of comparing ACOPF, high voltage solution, low voltage solution. The voltage limits were imposing, and the green dots is the second order cone. So we see that from minus 0.05, minus 0.05 to 0.05, where we are with a high voltage solution of the ACOPF. After that value, the ACOPF is infeasible with these voltage limits, but the second order cone, because all the inside of the ellipse is a feasible range, it provides these feasible solutions equal to the maximum, well, the upper bound voltage limit. Yeah, and that was it. Steven, I don't know if you want to perhaps give another note or any comment on the graph.
No, thank you. That's perfect. Very, very nice. Thank you very much, Carmen.
No problem.
Okay, great. So we will take a 5-minute break and we'll be back 12:11. All right.